answering by email. I'll leave some time at the end of the class also for some questions if we can, but just before we get started, does anybody have any questions about what happened to my video there? Okay. Oh, my video is giving me some problems today. Okay. Sometimes that happens. All right, it'll come back a little bit. All of a sudden, Zoom's giving me a hard time. Does anybody have any questions from last week's class? Everybody's good? Okay.
Yes, I send you question by mail.
Yeah, did I answer it?
No, I'm sorry. No. I sent it to you yesterday.
You sent me a question yesterday and I didn't answer
about the thermal forces.
Okay.
Which was not so fully understood.
Okay. Oh, I see. I said I'd review it in class. Okay. All right. Let me. Okay. Very quickly. So let me. Which part of the thermal forces? The whole thing you didn't understand?
Not the whole thing. I wrote you about the A. It was not. I did not understand what is the meaning of A, and about
A?
yes,
Okay.
and about when do we use. How do I say it? When do we use kilopascal or megapascal, and when do we use centimeters? It was not. I did not fully understand it.
Okay, so
the formulas and the A. What is the meaning of A?
Okay, so let me see if I can find my class notes. Let's see. Share my screen for the time being.
There were two examples, and in each of them you used another way to solve the problem, and it was not fully understood.
There is introduction to dynamic load. Okay, so let's see what I can do here. Okay, so let's go right to the examples then. By the way, A is the cross-sectional area of the rail. So let me do this. Okay. So if I go back here, the equation for the force is EA alpha delta T, where E is the modulus elasticity of rail steel. A is the cross-sectional area of the rail. Alpha is the coefficient of thermal expansion. And delta T is a change in temperature, the difference between the rail temperature and the neutral temperature. So let's see. So when we talk about A, we're talking about the cross-section of the rail. So if we look over here, for example, for UIC 60, the cross-section of the rail would be 76.86 square centimeters. For UIC 54, it would be 69.34 square centimeters. Right, so the cross-section of the rail varies depending on the weight of the rail or the size of the rail. So let's go. So are these the examples you said you were having some problems with, this example 1 and 2?
Yes, not the numbers, but you know, the libras and the kilopascal and everything. When do we have to use what?
Okay, so let's go back to the formula. Okay. E, the modulus of elasticity, is in megapascals or kilopascals, depending on which ones you want to use. The most commonly used value in the metric system is the 207 times 10 to the cube megapascals. So that's the a modulus of elasticity for rail steel. A is the cross-sectional area, and it's defined, again, depending on your units, in centimeters squared. Alpha is your coefficient of thermal expansion, is defined in 1 degrees centigrade. And delta T, your change in temperature, is defined in degrees centigrade. So if we go back to the problem here, okay, all my temperature is in centigrade. So my change in temperature is my rail temperature minus my force-free or neutral temperature. So in this particular problem, I said the air temperature is 110 degrees. I added 40 degrees up to it to get me a rail temperature of 150 degrees. Subtracted 50, and that gave me a delta T of 100 degrees. For the rail, the area was 72.6 square centimeters. The E, coefficient of thermal expansion, is 207. So not the coefficient of thermal expansion is 0.00000115 centimeters per degree centigrade.
Excuse me, why is it 40 Fahrenheit? Why not 50 Fahrenheit?
Which one here? Neutral temperature? Or
yes, this one. Why is it 40 Fahrenheit?
Because it's either 40 or 42. You'll see sometimes I use you should actually use 42 instead of 40. I use 40 in this example because it's also commonly used. 50 is too high. This comes from test data. When you go out and you test it in the field, generally it would be either 40 or 42. Actually, it actually varies between 30 and 42, but you tend to pick the highest value to be conservative. So,
yes,
okay. And so the force that's calculated comes out in kilonewtons. Does that answer the question? Are you still not clear, or do we need to go?
Just a minute. I believe so. So why do you use it? Why do you solve it for libras and why for kilonewton?
Because you're calculating a force.
Okay.
This is an equation for calculating the force in the rail.
So in kilonewton, you use 72.6 double hundred. And 72.6, it's in centimeters. Okay.
Oh, yes, because if you're using 207 times 10 cubes, that's in millimeters. That's equivalent to millimeters. So you got to convert back to millimeters. That's correct. Good catch.
Okay.
Okay. You should, if you work out there was an example in Moodle. Did you do the example in Moodle?
Yes, that's why I asked the question.
Okay.
Yes.
And so if you still have trouble with what you do in Moodle, because I've had a couple of emails and most people seem to have gotten it. If you still have trouble if you go back and try to do it again in Moodle, the problem in Moodle, if you still have trouble, just send me an email and I'll respond again.
Okay, thank you.
Okay, so now I want to get on to beam and elastic foundation. Why don't I see it? Oh, hold on a second. I have too many items open on my screen, so I have to close a few things here. Just bear with me for 1 second. Close dynamic load. Close dynamic load. All of a sudden my screen got too busy here. All right, now let's see if it works. There it is, good. All right. Good. All right. So what I want to do today is I want to talk about really one of the most fundamental models used in railroad engineering, which is beam and elastic foundation theory. I indicated earlier, and I keep repeating it, that my focus is not on how do you follow the standards, and there are a bunch of cookbook procedures out there, and I'll go over some of them as well. But I really want you to understand the engineering behind everything. So let's start off with a fundamental concept here, and that is, by the way, can everybody see the screen? It says railroad engineering on the top of the screen.
Yeah.
Okay.
Yes, we see.
Okay, good.
Alan,
Yes.
can you please turn your video on?
I'm having a trouble at the moment with Zoom. Zoom, at the moment, is not recognizing my camera. So I will try again in a few minutes. Sometimes it goes away, comes back. But I noticed that today, that every once in a while, Zoom does that to me.
Okay, not a problem. Thank you.
Okay, can somebody put themselves on mute? There's somebody there that's not on mute that I hear you talking in the background. So I just appreciate if everybody puts themselves on mute if they're not, and just take yourself off. Feel free to ask a question anytime, but just that way I don't hear background conversations.
Professor Zarevsky, just for the record, I joined you. It's Chagai Itzhaki. I'm with you, okay?
Oh, Hagai is here? Okay, very good.
Yes. Thank you very much. Sorry for
The only
interrupting.
one I'm missing right now is Vyacheslav Yudeshkin. Are you there? Okay. So, all right, we'll take care of that later. Okay. All right. So right now, when you talk about railroad engineering, there are really two different focuses. One is design-based engineering, where you're designing a new track, you're designing something new. For example, those of you working on a metro, for example, Neta in Tel Aviv, you may be designing your track. A couple of years ago, when I was working with JTMT in Jerusalem, we were designing the track. When you're working with a railroads that have been around a while, sometimes you're designing some track when you have a problem. So for example, I was just a couple of months ago, or I guess it was last year, I was called in for the design of by Israel Railways on the design of the Eastern route, the one that goes parallel to Kfish 6, the Highway 6. That there was some issues there with using some geotextiles, geocells in there. So that was design engineering. So when you're dealing with design engineering, you're dealing with what size rail, what kind of sleepers, what kind of ballast, what kind of sub-ballast, what kind of subgrade you have to work with. Do I need to put an extra layer of geomembrane or geocell or geogrid in there? And so those are all aspects of design-based engineering. And we're going to spend today, we're going to spend a bunch of time talking about that. But I want you to aware that a lot of railroad engineering, particularly if you're working for Israeli Railways or if you're working for an established railways, you're not building a whole lot of new lines so much as you're maintaining existing lines. And so you're really looking at maintenance-based engineering. And we're going to address that a little bit when we get into rail and other problems. Unfortunately, I'm not going to be teaching you about concrete sleepers and ballast and stuff in this class. That's Arcady's going to be doing that. But when we talk about rail, which I will be spending a lot of time, we'll be talking about a lot of maintenance issues. But it's really a different focus and approach, and we'll talk about the differences here a little bit. But railroad design engineers. So those of you who are consultants, and I know there are a lot of consultants out there, you're probably dealing a lot with design engineering. Railroad field personnel, railway engineers, tend to spend more time talking about maintenance. So if you go to a big railroad, be it the British Rail, Network Rail, or the Deutsche Bahn, or the Union Pacific in the United States, or Chinese railways, and they're a big major railway operation, most of their engineering people are concerned with maintenance. How do you fix defects that develop into the track? How do you correct geometry? How do you correct rail problems? As opposed to how do you design the track from scratch? So there are really two different approaches. And so I want to differentiate with that. Now, for a moment, I want to focus on design-based engineering. We'll do maintenance as well, but I want to focus today about design-based engineering. And there you're concerned with, as I said, what components do you use? What dimensions do you use? What size rail? What size sleepers? What type of fasteners? What type of, how deep is your ballast layer and your sub-ballast layer, etc. Now, there are standardized tools out there. So the ARIMA manual, I've referred to the ARIMA manual for a couple of times. That's the manual of recommended practices for the American Railway Engineering and Maintenance Away Association. It's a 8-volume set that takes about 1.5 meters of space on my bookshelf, and it's an extremely comprehensive manual, but it's geared towards the heavy axle load world. There are UIC and EU standards and tools out there. There are a couple of good reference texts out there. Probably the best 2 reference texts are Conrad Esveld's book on railroad engineering and Arnold Kerr's book on railroad engineering. As a matter of fact, when we talk about beam and elastic foundation, Arnold Kerr. So the 2 best books on railroad engineering would be Esveld's book. Esveld used to be a professor at the Delft. He's since retired. Do I hear, is somebody asking me a question, or is there somebody just talking in the background there? If you're talking, please put yourself on mute. So Esveld's text, Conrad Esveld, like I said, formerly from the Delft University in the Netherlands, also formerly from the Netherlands Railways. And then the other book, Railway Engineering by Arnold Kerr. He was an American professor. Actually, he was at the University of Delaware a couple of years before me, but he was actually my professional mentor. I knew him for about 60 years, well, not quite that much, 50 years before he passed away only a couple of years ago. But what I want to start with is modern railroad engineering theory. And that really starts with something called beam and elastic foundation theory. So beam and elastic foundation theory says that I have a rail, and then everything underneath the rail can be treated as an elastic foundation. So the rail is a beam, a structural beam, and then the sleepers, the ballast, the subgrade can be replaced by linear elastic springs, continuous springs. So that you see here, this beam over there is my rail. These springs over here represent my sleeper, my ballast, my sub-ballast. This represents my loading up here. And this is my representation of the beam and elastic foundation theory. And I can use beam and elastic foundation theory to calculate my rail stresses and my deflections. And then in turn, I can start calculating my loads onto my sleepers. And then that ultimately will be the foundation for calculating my loads on my ballast and my sub-ballast. And, we're going to go through that today, how you can actually calculate the deflections and stresses in the rail, convert that to loads going into the sleeper, convert that into loads going into the ballast, and ultimately reduce the loads down to where they can become the subgrade. There have been other models used, different foundation models, and we'll talk about those later on, that introduce more sophisticated elements. But realistically, beam and elastic foundation theory has withstood the test of time, and it's used to this day for analyses. For example, when I was doing the work on the East Line of Israel Railways, I used beam and elastic foundation to develop the load distribution that was going ultimately into the ballast and into the sub-ballast to determine what support conditions I need underneath and what type of additional design features I need to add to reduce the stress levels. So beam and elastic foundation theory, like a lot of things in the railway industry, dates back to the 19th century. It was initially introduced by a fellow by the name of Winkler in 1867, but additional work has been done through the 20th century. So if you take a look, you'll see some really famous mathematicians and engineers have been involved in this. Timoshenko, who's sort of the father of engineering mechanics, so to speak, worked on railroad track design using beam and elastic foundation theory. Hatenyi, another big name in structural mechanics, worked on beam and elastic foundation theory. Hatenyi was just around the 1950s, I guess. Kerr worked things to sort of the 1970s till about 2000. And by the way, it was his textbook that I was recommending, one of the two, his and Esvelt's. And so beam and elastic theory has been used, modified, improved upon, etc. Okay. So I'm going to give you a little quickie introduction into the differential equations behind it. It's important enough that I want you to at least understand a little bit the theory behind it. I'm not going to test you so much on the theory, but I will tell you right now, beam and elastic foundation, the application of that will be on the exam. I absolutely expect you to know that. There is an assignment to work on this that's in Moodle, and you're going to want to spend a little bit of time on this because the place, and just to give you fair warning, this is probably the place that more people get wrong on the exam than any place else because they don't spend enough time practicing or getting it done. So I consider this to be absolutely fundamental to your understanding of railway engineering. And while it's not in any of the standards, it's really a real basis of real engineering design. And so I expect you to know it. Okay, so there are lots of variations of it, but it's in its most basic form. Beam and elastic foundation is a fourth order ordinary differential equation, where this really is the beam term, which the beam think of as the rail. So you have EI, E is the modulus of elasticity of the rail steel, I is the moment of inertia of the rail, and EI combined is often referred to as the flexural rigidity of the rail. W is the vertical deflection at the rail. W of X is the vertical deflection of the rail at point X. D to the fourth W, dx to the fourth is the fourth derivative of W. KW is your foundation term. So going back here, the EI dW to fourth, dx to the fourth is really your beam term, which is the rail. And your KW is your flexural term, where K is the stiffness of this foundation. Sometimes you'll also see it in some of the literature referred to as U. I'm going to use K for the most part, but like I said, you'll see it both. And Q of X is a general distributed loading, which we're going to replace very quickly. We're going to replace with a simple wheel, which becomes a point load. So the problem we're going to end up solving and working with is this beam and elastic foundation subject to a wheel. So let me make sure I got that. You're clear on that. I'm going to replace a distributed load with a single wheel, and that's going to be an applied vertical load. And then we're going to learn how to handle a bogie. Then we're going to have to learn how to handle a wagon. We're going to have to learn how to handle a three-axle locomotive bogie, etc. We'll get into that as well. Okay. So hopefully you're all familiar with the notation. This equation, this notation W to the fourth is the same as this. It's just a shorthand notation just to save me time in the writing. So this is still EI d fourth to the W dx to the fourth plus KW, except I've now gotten rid of the distributed load, like I said, and I've replaced the distributed load with a single wheel load of force P. So my equation is EIW d to the fourth W dk to the dx to the fourth plus KW equals 0. And now it's a fourth order ordinary differential equation. I need 4 boundary conditions. If I pick my x equals 0 point to be right where my wheel is, so at x equals 0, I have my wheel. So my 4 boundary conditions as at x equals 0, the slope is 0. Why? Because it deforms symmetrically under the wheel. The track is symmetric. So if it's symmetric, it means the instantaneous slope is going to be 0. I know the force P here. So if I do a free body diagram, I have P over 2 on this side and P over 2 on this side. So my shear force at x equals 0 is P over 2. And my shear force is EI d cubed W dx cubed at x equals 0. And that's equal to P over 2 from my free body diagram. And then I know that at x equals infinity, my deflection is 0, and at x equals infinity, my slope is 0, because this damps out at some point. So I now have 4 boundary conditions. The classical solution to this fourth order ordinary differential equation, when this is 0, and I have the 4 boundary conditions I just defined, is this. This comes back to both Winkler and Timoshenko and many others worked on this one. And then I can apply the boundary conditions and I get C1 equals C2 equals C equals P beta over 2K. I'm not going to solve this for you. For those of you who are inclined to do so, you're welcome to do this. What you'll see is C3 and C4 drop out. C1 equals C2 is equal to P beta over 2K. And lo and behold, you end up with this answer. So there's my 4
IV.
Say again.
The IV.
Explain what?
The IV. You wrote. One page before. Yes, this IV. What do you mean by this?
Oh, this?
Yes, IV,
This is a short, it's been a long time since you've done differential equations, right? This is a shorthand, this is a shortcut for writing this. When you get tired of writing this all the time, the fourth, d4w dx to the fourth, in classical differential equation literature, you write this, w to the fourth. So IV is a Roman 4. So it's basically the same term as this, d4w dx4. It means exactly the same, it's just a different way of writing it.
Okay.
So you're not responsible for knowing this derivation. I wanted you to see that, I just wanted you to see it once, because every once in a while I get somebody who's interested in enough into it to know it, but you are very much responsible for this. So here's my fourth order differential equation again, Q equals 0. And then we solve with the four boundary conditions like I showed you, and you get this answer. W of x is equal to P beta over 2K e to the minus beta x cosine beta x plus sine beta x, where beta is the fourth root of K over 4 EI. So let's go over our units. K is my foundation stiffness, in kilonewtons per millimeter, which is also in pascals. E is the same modulus of elasticity of rail steel we talked about when we were doing thermal forces. The modulus of elasticity of rail steel is a constant. I is the moment of inertia associated with the rail section, and it's the vertical moment of inertia. So if I have a rail section, since I'm doing deflection in the vertical plane, it's around the neutral axis and this neutral axis. It's the moment of inertia around that neutral axis. And again, it's standardized, it's tabulated. You'll just look it up on a table. So that's beta. P is the wheel load, the dynamic wheel load if the vehicle is moving. The only time you use a static wheel load is if I tell you the vehicle is standing still and velocity is 0. Once I give you a velocity, use a dynamic wheel load. And for this class, if you use the ARIMA formula, which we went through last week, that's fine. If you want to use a different formula, you just have to tell me which formula you're using and we'll check it out. But P is always a dynamic load because the railroad world is dynamic. So this is my deflection. W of x is P beta over 2K e to the minus beta x cosine beta x plus sine beta x. For a single wheel, okay, I'll come back again. For a single wheel, it turns out the maximum deflection happens under the wheel at x equals 0. And if something very interesting happens when you put an x equals 0, this term drops out because the sign of 0 is 0. This term becomes 1. This term becomes 1. And my deflection at x equals 0, or my maximum deflection, is nothing more than P beta over 2K, where again, P is the dynamic load, beta is this term down here, the fourth root of K over 4 EI, and K is and K again appears over here, which is again my track stiffness. So that's my deflection. I can also calculate my moment, which I'm going to need if I want to calculate stresses, right? So my moment, the moment, if you remember correctly, is nothing more than EI times the second derivative of W. So for those of you who are not familiar with that term, WW double prime is the second derivative and if we take this, and if you go back and you take the second derivative of this and solve for it, you end up with the moment is equal to minus p over 4 beta e to the minus beta x cosine beta x minus sine beta x. And that's my moment equation, where beta is exactly the same as we said before, the fourth root of k over 4 ei, and p still the dynamic load. And the maximum moment under a single wheel likewise occurs at x equals 0. And so at x equals, so the maximum moment, the same thing happens. This drops out. This becomes 1. This becomes 1. And so my maximum moment at x equals 0 is nothing more than p over 4 beta. And if you want a shear load, the shear load is the third derivative of the deflection. So again, W triple prime is equal to D cubed W dx fourth. And by the way, I'm giving you all this so that you don't have to do the derivatives. I'm not expecting you to do differential equations in this class, which is probably a big sigh of relief to everybody out there, because most of you probably haven't done differential equations since you graduated college. But the shear force, which is the third derivative, is minus p over 2 e to the minus beta x cosine beta x. And now to check to see everything works, if you take the maximum shear force at x equals 0, this becomes 1, this becomes 1, and my shear force is minus p over 2, which, if you remember correctly, was our boundary condition. All right. So now what does all this mean, and why do I care, and why am I interested, and how do I use it so I pass the exam, and how do we do all this stuff? Okay, so let's take a moment. Going back to the deflection curve. So now we're going to go back to the deflection curve, and let me clear this mess up here.
Can you please repeat what beta is before you continue?
Say again?
Can you please repeat what beta is before you continue?
Beta is this, right over here.
What is it?
It's
Just
the fourth root of k over 4 ei, where k
it's
is
not some kind of a force.
beta is a is a constant in the units of 1 over millimeter.
Okay.
So if you were to do so let's do a unit check. It's always good to look at units, right? So you understand what it is. K is in newtons per millimeter squared. That's my units for stiffness. And we're going to talk about that. I'm going to spend a little bit of time talking about K. E, my modulus of elasticity of rail steel, is also in newtons per millimeter squared. So in fact, from a unit point of view, these two cross out to each other. I is in millimeters to the fourth, right? Most of you should remember that. So I have the fourth root of 1 over millimeter to the fourth. So my unit then becomes 1 over millimeter. Now, how do I know that's right? Well, let's go back up here. If I have cosine beta x, I know x is my distance along the track. So x is in millimeters. And I know I have to be non-dimensional if I'm going to be in a cosine or a sine or an exponent. So therefore, beta is 1 over millimeter, and 1 over millimeter times millimeter crosses each out. And now I've just checked my units. And by the way, that's all. If you're running into an equation and you're not quite sure how the equation works, it's not a bad idea to check your units and make sure your units work out. You'll very quickly see if you have a mistake or not. So
Okay.
if I solve this equation, W of X equal to P beta over 2K, e to the minus beta X, cosine beta X plus sine beta X. And I set, so remember I have a single wheel over here. And this is X. So this is my X value. X equals 0 is directly under the wheel. I just said that. That's the way I've done that. Then my deflection looks like this. My maximum deflection, which is actually P beta over 2K, is, you can see for this problem. So in this particular problem, I have UIC 60 rail. I have a track modulus that's just under 7 megapascals. And I don't define the load here for the moment. Let's just say it's a UIC freight vehicle moving at a given speed. So you can see the deflection here is of the order of what, 8.5 millimeters under the wheel maximum. And then decreases under the wheel. Now look over here. This is very, very, very important. This is my W equals 0 line right over here. Look what happens over here at X equals 4,000 millimeters. My deflection has gone up. It's going negative. I'm actually picking up the track. If you go out and look at you look at a piece of railroad track and watch a train go by, you will actually see the track deflect under the wheel. But ahead of the wheel and behind the wheel, so here's ahead of the wheel and here's behind the wheel, you will actually see a little bit of an uplift wave. And that uplift wave is actually picking up the track a little bit. Not a lot. We're talking about here, what, 1/3 of a millimeter? So we're not talking about a big uplift in this particular case, but we do get this. You don't, it's harder to see in concrete tie track because the weight of the sleepers hold it down. But in wood tie track, where you have cut spikes, and so there's a gap between the rail and the sleeper of the order of maybe 4 to 6 millimeters, you can actually see that movement very clearly under the train. It's a very, very visible movement. And we're going to talk about its effects later on because it has a lot of consequences in terms of things like track buckling and other behavior. And so one of the reasons track buckles underneath the train is because you get this uplift wave that picks the track up a little bit from the bed ballast, maybe only a fraction of a millimeter, but just enough to reduce or eliminate the friction between the base of the sleeper and the ballast. And that reduces the resistance of the ballast to track buckling. And that's why you'll tend to see track buckling underneath the train, which we know happens, or immediately ahead of the train. So there are a lot of different phenomena that we see in the railroad track that are tied into this uplift wave. So we actually know this happens. This is pretty important. I'm going to show you how to do this calculation in a few minutes, so don't worry about it. We'll go through this carefully. I'm going to spend a lot of time on this. But I want you to understand what the shape. So this is under a single wheel. Here's another view of it. Same one, except I'm just, in this particular case, I'm just showing you from X equals 0 forward. But again, you see the maximum deflection, you see the uplift wave, then you see the uplift wave tapering away. And then by the time you get about 8 meters away from the wheel, for a single wheel, there's no real effect. Now, if I take the moment, so let's go back to my moment equation. If I go back to this equation, moment equal to minus P over 4 beta, eta minus beta x cosine beta x minus sine beta x. And again, the same thing. We set the wheel at x equals 0. Then my moment curve looks like this. Again, this is a single wheel right over here. My maximum moment occurs at x equals 0, and my maximum moment value is P over 4 beta, minus P over 4 beta, just like we talked about. So you can see the maximum moment here. Again, this is my moment equals 0 value. And again, you notice I get a significant reverse moment. And this reverse moment means that I get a reversal in stresses. And this becomes really important. And we're going to talk about it when we talk about rail. Because what's happening in the rail is this uplift effect is basically giving you a stress reversal. So, for example, under the wheel, I have a moment that basically puts my base in tension and my head in compression. And then when I have the reversal, I flip. My moment flips. And my head goes into tension and my base goes into compression. What that means is I'm getting reverse stress, which means I have a potential for fatigue. And it's more than a potential fatigue, as I will spend a lot of time on it. This is one of the causes of rail fatigue. This is one of the contributing factors to rail fatigue, which is a major issue and one of the most major failure modes in rail, and cause of derailments and failure and rail replacement and all sorts of good things like that. And to understand that, you have to understand this moment reversal. Is everybody clear on this? Again, if I were to just take half from x equals 0, again, here's my moment. You can see the maximum moment is about 55 kilonewton meters. My reverse moment, which tends to be for a single wheel, which tends to be about 21% roughly of the maximum moment. Then you can see it comes back down, dissipates already, and then by about 8 to 10 meters, it disappears and there's no effect there. By the way, really important, the reversal point, you notice where it goes from negative moment to positive moment is here about a meter, about 1,000 millimeters. Here, it's about 3 meters, about 3,000 meters. The reversal point for the deflection and the reversal point for the moment are not the same. The curves behave differently. And that will come in later when we talk about what happens when we deal with a bogie as opposed to a single wheel. So this is just repeating what I said before. Maximum moment at W0 is P beta over 2K. This is P beta over 2K. Excuse me, maximum deflection. Sorry, I said moment. Maximum deflection is P beta over 2K. Maximum moment is P over 4 beta. This is P over 4 beta. Okay, so let's talk about some of the input terms that we're dealing with. There are really four major inputs into the equation: P, K, E, and I. Okay? E is my modulus of elasticity of rail steel, and that's fixed, and that's constant. And basically, for all rail steels, it's basically the same. In fact, when you're dealing with premium rail and standard rail, the E's are basically the same number. It doesn't change significantly. So E for rail steel is always the same, 207 times 10 to the cubed. The other three will vary. So P is my dynamic load. And as I said previously, for all practical purposes, you're best off using the ARIMA formula for this, because I happen to like the ARIMA formula and it works very well. And I like it better than most of the European formulas I see, other than going into the very sophisticated P1, P2, or dynamic models equations, which we're not going to do in this class. Those are much more accurate. But if you want something simple and easy to use and something we can apply in class very quickly, we'll use the ARIMA model, which by now you should be familiar with since you had an assignment with it. So at 50 kilometers per hour, it's about 1.28 times static. At about 80 kilometers per hour, it's about 1.46 static if you're using a 914 millimeter wheel. If it's a different wheel, then these numbers are going to change a little bit, because P is a function of the speed and the wheel diameter. Okay. Track modulus, again, we're going to come back to this, is the support stiffness of the track. It's basically the sleeper, the ballast, the sub-ballast effect, which we're converting into this continuous linear spring. And the rail section is the moment of inertia of the rail section that you're using, of the rail size. So let's talk a little bit more about track modulus. So track modulus is defined as this continuous strings. Now be careful. We're talking about a continuous spring, not a discrete spring. So this is not the case where I have a spring here, and then 2 meters or a meter away, I have another spring here, and then another meter away, I have another spring here. This is where I'm basically treating this as a distributed spring. And as I mentioned, we refer to it as K. Sometimes you'll see it also referred to as U in the literature. They're both the same, interchangeable. And because it's a continuous spring, it's the deflection under load per unit length of track. So it's newtons per millimeter, which is this spring deflection. This would be newtons per millimeter right over here, but it's along the length of the track, so it's per millimeter again. So it's newtons per millimeter squared, or pascals, megapascals, whichever unit you want to use it in. Pascal is defined in terms of newtons per millimeter squared. And there have been a huge number of tests that were done over the last 100 years. In fact, there was a massive collection of tests that were done in the 1940s, 50s, and 60s, where they went out and did literally thousands of tests. There's a book called The Talbot Reports by A.N. Talbot. That's about, I'd say it's about 1,200, 1,400 pages long. And it's just nothing, it's full of test data. There's test data after test data after test data. So in general, the K value is going to be roughly between 3 and 50 megapascals, with very poor track or very soft track being at the lower ends, and very stiff track or very good hack being in the top end. So if you have good concrete sleeper track, by the way, remember tie and sleeper are the same thing. It's just different terminologies. So if you have good concrete sleeper track on good ballast, you're looking at about 30 to 50 plus megapascals. By the way, if you have a slab track, so like if you have a tunnel track or if you have a slab track that you're building for your metro, like Tel Aviv is building slab track in the tunnel, and Jerusalem, it's pretty much embedded track throughout the street. The stiffness can even be higher. For heavy tunnel track, the stiffness could be of the order of 70 or 80 megapascals, which is very, very stiff track. And that has all sorts of consequences in terms of distribution of load and something like that, which again, we're going to talk about a little bit later. So good concrete sleeper track is about 30 to 50 megapascals. Good wood sleeper track or poor concrete sleeper track. Concrete sleepers on a poorer ballast subgrade combination will be about 20 to 30 megapascals. Why does good wood equate to not so good concrete track? Because concrete sleepers are about, and we talked about this, I think, in our earlier class, are about 3 times the weight, 3 to 4 times the weight, depending on where in the world you are. I think in Israel it's probably 3 times the weight of a wooden sleeper track. So it pre-compresses the ballast, and so it makes the track stiffer. Think of it, think about it, go back to your beam and elastic foundation stiffness. And if you put a heavier load down here, you're gonna compress that spring a little bit. It'll be a little bit stiffer because the springs really are a little bit nonlinear. So good wood sleeper track or poor or moderate concrete sleeper track is 20 to 30 megapascals. Poor support conditions. If I have a lot of mud, if I have a swamp, if I have a peat bog, if I have really, really poor support conditions, my track modules can be as low as 3 to 10 megapascals, 3 to 7 megapascals for that type of behavior. And that, as I will show you in a minute, has major ramifications in terms of how much the track will deflect, how much stresses you will get, etc. Obviously, the softer the track, the more the track is going to deflect, and as you'll see, the greater the level of stresses. So, the greater the range or the variation of stresses. Actually, the stresses go the other way. So that's my track modulus. The other parameter I have to deal with is my moment of inertia. Just like we dealt with A for the thermal forces, we're going to deal with I for the moment of inertia here. And so the moment of inertia is, again, the vertical inertia around the neutral axis in the vertical plane here. So you can have a different moment of inertia if I have different rail section sizes. So UIC 60 is bigger than this has S54, but there's also a UIC 54, which is very similar, and there's an S49. I don't think there's a UIC 49, there's a UIC 50 out there. And then the British have their own sections as well, and some of the French have their own sections. So there's a range of sections out there. And the greater the weight of the rail, the greater the height of the rail, the greater the moment inertia. So if we look at this table of rail, so just put it in reference, 100 RE rail is about 50 kilograms per meter. 150 RE rail is about 62 kilograms per meter. 141 RE rail is about 71 kilograms per meter. These are heavy axle load rail sections and North American rail sections. Well, actually, the heavy axle load sections are really here. These are lighter sections. Here's UIC 54 and UIC 60. UIC 50 is very similar to this, not exactly the same, but very similar to this. Come back over here. Moment of inertia about the neutral axis for UIC 54 is 2,346 centimeters to the fourth. And UIC 60 is 3,054 centimeters to the fourth. So you can see the heavier the rail section, the greater the moment of inertia. That's just a lookup table. I don't expect you to memorize this, but everything I do is going to be open book. By the way, the exam will be open book as well. Open book, open notes. So you'll have access to all your notes for the exam. So let's do a calculation. And you know what? Rather than try to do it on there, let's do it on a spreadsheet. If I can find my spreadsheet. Okay. So let's do a beam and elastic foundation calculation here. So let's start off with the problem. I have a 90-ton wagon, standard freight wagon, standard UIC wagon, 22.5 metric ton axle loads, 11.25 metric ton wheel loads. Now, by the way, for these analyses, when we deal with beam and elastic foundation, we're dealing with the wheel load, not the axle load. So we're always dealing with the wheel load. So I have 4 axles. Oh, let me do it this way. I have 8 wheels, standard freight wagon, okay? So my 90 tons, my static wheel load is nothing more than my weight of my car divided by the number of wheels. And that becomes 110 kilonewtons. If my vehicle is going at 80 kilometers per hour, my wheel diameter is 915 millimeters. My dynamic wheel load is 160 kilonewtons. So basically what I did here is I just converted tons to kilonewtons to newtons, divided by 4 axles, 2 wheels per axle, which gave me my 8 wheels. And then I apply here the ARIMA formula, 1 plus 5.21 times my speed, 80 kilometers per hour, my wheel diameter, 915 millimeters, multiplied by the static wheel load. Everybody clear so far what I did here? Any questions? All right. I have UI 60 rail. If I go back to my chart, I can see that I get 3,055 square centimeters. My modulus of elasticity is 207 times 10 cubed, or 2.07 times 10 to the 5th megapascals. C is the distance C is the distance from the base of the rail to the neutral axis. That's how it's defined. It's the distance from the base of the rail to the neutral axis. And that same table I showed you a moment before. In fact, let's go back and just make sure you know where you see everything here. This is C, the height of the neutral axis above the base. So for UIC 60, it's 8 centimeters. And this is H, the height of the rail, 17 centimeters. So this is the same sheet you were looking at a moment ago. C is the 8 centimeters or 81 millimeters. H is 17 centimeters or 172 millimeters. So what we're just talking about right here. K is the track modulus, which I'm defining here. I was an input I will give you is roughly 6.9 megapascals. Beta, we now have enough information to calculate beta. Remember beta, the fourth root of K over 4EI. So beta is equal to the fourth root of K, which is 6.9 megapascals, divided by 4 times E times I. Now we have to bring everything into millimeters. Remember, we have to be consistent because all our units, megapascals is in millimeters squared. So my I has to be converted from centimeters to millimeters, which is that conversion. So there's my beta. K divided by 4 divided by E times 10 to the 4th, because I got to convert it from centimeters to millimeters. Sorry, I have to convert, sorry. E is in the correct unit, sorry. I has to be converted to from centimeters to millimeters. So that's why there's a 10 to the 4th there. Everything now is in millimeters. And so we have my beta is equal to 0.00072 times 1 over millimeter. Any questions here? Anybody understand or have any questions about what I just did to calculate beta?
I have a question, if I may ask.
Yes.
Can you show in one of your slides the C and the H? I wasn't able to follow up. Thank you.
Okay. Let's clear the screen. Okay, let's take my UIC 60 rail, right?
Mm-hmm. Yeah.
So this is my height of my rail, 172 millimeters. That's H.
Okay, and C?
And C, remember your neutral axis of the rail?
Okay.
C is the distance, between the base of the rail. Let me clean that up so I don't make, I'm a little bit sloppy today. C is my distance between the base of the rail and the neutral axis.
Okay, yes, I see.
And it's a standard tabulation. Every rail manufacturer has a standard book of tables. UIC puts out a standard book of tables for UIC rail. The British put out a standard book of table for their rail sections. ARIMA, RE means ARIMA. So UIC means it's a UIC rail section. RE means it's an ARIMA rail section. ARIMA and the ARIMA manual has a standard book of sections. Quite honestly, you just go to every rail manufacturer will tell you what their properties. These are all tabulated. You're welcome to try to calculate it if you want, but you don't have to. So C is always one of the properties given, and it's always given as the height from the base of the rail to the neutral axis. And again, H is just the height of the rail itself. Is that clear?
Yes, thank you.
Any other questions?
I have another one. You decided the K?
I gave you the K. Now, I will
Okay.
talk about later in the class, I'll tell you how you find K.
Okay.
You can measure K in the field. You can go out to a piece of track and measure K, and we're going to talk about that later in the class. But for this class, for any problems I give you, I'll give you K, because measuring K in the field is a difficult process. It's not an easy process. I've done it many times, but it's not an easy process. Okay. So everybody is clear how I got beta. Everybody's clear how I got P dynamics. Now we can go ahead and we can calculate. So let's come back over here. And we want to calculate the deflection and the moment. Those are really the two most important variables you're going to deal with. Deflection to understand how much your track moves, and the moment to understand not only the moment, but the moment allows you to calculate the stresses in the rail. So the bending stresses in the rail. So the two most important calculations you need for your track are the rail deflection and the rail moment. So again, for this particular case, remember the wheel is sitting right over here at x equals 0. So I'm going to do a calculation from x equals 0 onward, which is the symmetric half. And then you can just as easily have done it for the negative half, or show the net, put a negative value in there. But for this problem, I'm just going to do this. I'm just going to do the symmetric half. Okay. So what you can see is what I did here is I just did a spreadsheet, and you can do it vertically, horizontally, I don't care. X equals 0. I've gone out 6 meters for the moment. You can go out longer depending on the problem, but I've done every 100 millimeters. Now, you can make this a finer mesh. You can make it a coarser mesh. You don't want to make it too much coarser. You don't really want to go out every meter or every half meter, for example. That's really too far apart. Even 100 millimeters is fairly far apart because the numbers change within them. And I'll show you that in a minute or two. But for x equals 0, 100, 200, I calculate my deflection. This is my P beta over 2K e to the minus beta x cosine beta x plus sine beta x, which I showed you in the previous sheet. Okay, so these, we've already calculated everything here. P is P dynamic. Beta, we just calculated over here. It's the 4th root of K over 4EI. K, is a support. So again, the deflection is P beta over 2K e to the minus beta x cosine beta x plus sine beta x. Now, please be careful with how you put your parentheses, because everybody makes a mistake one time or another on that one. But again, there's a work problem. The work problem is set up the exact same way. I strongly suggest the first page of the work problem will be the problem itself, and you can work on that without looking at the answers. the second tab will be the answers for the single axle problem, and the third tab will be the answers for the two axle problem, which we haven't yet discussed yet. So anyway, by putting up in the spreadsheet, now I can order, so this is automatically W of 0, which, by the way, you can see I cross-checked over here. W of 100 millimeters, W of 200 millimeters. This is the plot. You can see at roughly X equals 4,000 millimeters. Down here, it's actually closer to about 3,800. Actually, it's right over here. So the maximum deflection you can see is, okay, so sorry, well, let's go back here. You can see the maximum deflection is actually closer to about 3.5. Oh, I'm looking at moments. Here's my maximum deflection underneath the wheel, 8.4. My maximum reverse deflection is actually, sorry, it's about actually 4,200. You can see it's 0.350, 0.359. It's about 4,200. And again, you got to be a little bit careful here on how many sensitivities, because watch what happens. Let me do the whole thing here because this is going to have to follow. If I wanted to have, you can see it's changing. Now, in this particular case, I should have actually come between 42 and 43. So let's do the same thing here. You can see how it's changing. And so it looks like my maximum is actually probably going to be here. Oh, what did I do? Oops, I didn't do enough. Let's just do this. So you can see, I probably would have to go out to another decimal point to see where my maximum is. So you can see in this particular case, my maximum is actually at 4350. So, but it's out to the fourth decimal point, so it's not a big difference. So this is my deflection. My moment, I get the exact same way, except I use my moment equation, which is P over 4 beta e to the minus beta x cosine beta x minus sine beta x. And by the way, if you notice, I always use absolute value of x because if I wanted to go to x equals minus 2,000, and if I didn't use the absolute value, I'm going to get garbage, because the sign of minus 2,000 and the sign of the absolute value of minus 2,000 are not the same. So my moment, again, you can see my maximum moment here. And again, here, my reverse moment is happening. You can see it goes from plus 555. My maximum reverse moment is actually about right over there, about 2.2 meters or 2,200 millimeters. I'm going to come back to the stress later. We're not talking, I'm going to hold off talking about stresses for a few moments. We're going to come back to the stress discussion later. I just want to stop now and make sure everybody understands this, and then we're going to take a break, because this is a good place to take a break. I want to make sure everybody is clear on what I've done over here. Any questions on how do I calculate deflection and moment, and how I get my deflection and moment curve? Now, I'm sure you don't all understand it perfectly, which means nobody really is comfortable until they want to try practicing it on the work problem and then want to ask me. So feel free to ask me a question. We can take, we can come back to this later. We will come back to this later, but I just want you to make sure you understand how to do this.
Alan, can I ask a more general question?
Yeah.
Will we need to be able to develop these equations, or just to
apply it? All you need to do is to apply it. No, I don't expect you to be able to, I don't expect you to derive the equation. I wanted to show you the derivation real quickly because I like to go at least a little bit of depth to remind you guys all that you are all graduate engineers and we're just not using formulas that a high school student can use. I don't really expect you to rederive the equation. Anybody wants to try? If any questions, feel free to do this. No, what I do expect you to do is to do what I'm showing you right over here. That's I do expect you to do.
Will we need to develop a graph, or will we need to?
Yes, you will need to develop a graph.
In the exam?
The exam's a take home. Well, I don't know if it's gonna be take home or on the spot, but yes, the exam is gonna be open with the computer. Yeah.
Okay. So you will ask us, for example, like at what x, what is the deflection? What is the moment at a specific point?
So an exam, for example, I will ask you, what's the maximum deflection? What's the maximum reverse deflection? Where does it go from positive to negative? Where does it come back down? Where does it do that in the moment? So I'm going to expect, I'm going to expect you to be able to solve. I'm going to expect you to be able to find this reverse moment. I understand we're not going to have printers available in the exam, so we're not, I'm not worried about an accurate exam. Sometimes I do ask you to draw something by hands to make sure you understand it. But when I do ask you something, I will for sure be asking you where the maximum reverse moment is, where the maximum reverse uplift or reverse deflection is, where it changes, where it goes across the 0 point. So for example, if you wanted to see this point over here, you would come back here and you can see that it happens between 3,200 and 3,300 millimeters, right? It goes from minus 50 to minus 30. So it's probably happening somewhere around 3,260 or 3,270 millimeters is where it's going from in the deflection, where it's going from here to here. The reverse moment is happening roughly around 1500. So the reverse moment is happening right there.
Okay.
500,000. You see how it's going from positive to negative? So that's where it flips. We already talked about the maximum reverse moment. That was about over here. No, over there. Okay?
So we build this type of Excel before the exam as a preparation to the exam?
No, you're going to have to do it in the exam.
The exam to build this Excel.
Yeah,
Okay.
which means you better practice this a little bit.
Yeah, I understood. Thank you.
Okay, any other questions? Let's take a 15-minute break and we'll reconvene around 1:45.